A Nash equilibrium is a set of strategies, one for each player, such that no player can increase his or her own payoff by changing only his or her own strategy while the others keep theirs unchanged. Pure strategy Nash equilibrium. Each player chooses a single action with certainty. Formally, let S sub I be the finite set of actions for player I, and U sub I colon S sub 1 times times S sub n to the set of real numbers, the payoff function. S star equals open parenthesis S star sub 1, comma, S star sub n close parenthesis. Ui of S star minus I is greater than or equal to Ui of Si, S star minus I, where S star minus I denotes the actions of all other players. Mixed strategy Nash equilibrium. Each player randomizes over his or her pure actions. A mixed strategy for player I is a probability distribution sigma sub I over S sub I. Ui tilde of sigma 1, comma, sigma n equals the sum over S in S of Ui of S times the product from J equals 1 to n of sigma sub J of S sub J. Ui tilde of sigma star minus I is greater than or equal to Ui tilde of sigma star minus I. The concept is useful in many business situations. For example, two competing airlines choosing whether to fly a lucrative route, pure, or to randomize flights to keep competitors guessing, mixed. A best response function tells a player which actions give the highest payoff, given what the others are doing. For player I, the best response correspondence is Br sub I of open parenthesis S minus I close parenthesis equals the set of Si in Si such that Ui of open parenthesis Si comma S minus I close parenthesis is greater than or equal to Ui of open parenthesis S prime I comma S minus I close parenthesis for all S prime I in Si. When all players choose actions that are best responses to each other, the resulting strategy profile is a Nash equilibrium. Analogy: imagine a group of friends deciding where to eat. Each friend's best response is the restaurant that gives them the most enjoyment given the others' choices. For example, they want to be with the group but also like the cuisine. The final dining spot is a Nash equilibrium if no one would switch to another restaurant after seeing the others' decisions. In practice, you can draw a best response curve for each player, often on a graph, and look for the intersection points. That intersection is where each player's choice is optimal given the other's choice, the Nash point. Explanation: the Nash existence theorem, proved by John Nash, 1950, states that every finite game, finite set of players, each with a finite set of pure strategies, has at least one mixed strategy Nash equilibrium. Key conditions: 1. Finite number of players. 2. Each player's strategy set S sub I is finite. 3. Payoff functions U sub I are real valued for every pure strategy profile. Proof sketch using Kakutani's fixed point theorem. Convert each player's mixed strategy set delta S sub I, the simplex of probability distributions, into a compact convex set. Define a correspondence R delta S sub 1 times delta S sub n maps to delta S sub 1 times delta S sub n that maps each mixed strategy profile to the set of best responses for all players. Show that R has a non-empty, convex valued and closed graph, the technical requirements of Kakutani's theorem. Kakutani guarantees a fixed point sigma star such that sigma star is in R of sigma star. By definition, this fixed point is a mixed strategy Nash equilibrium. Business intuition. Even in a market with many firms and many possible pricing or product mix choices, there is always one way for the firms to randomize their strategies so that none has an incentive to deviate. This assures analysts that equilibrium analysis is not empty. A solution always exists in theory. The theorem also motivates the use of mixed strategies when pure equilibria are missing, as often happens in competitive advertising or auction settings. Explanation: to find pure strategy Nash equilibria in a normal form matrix game, follow these steps. Write the payoff matrix dash rows for player 1's actions, columns for player 2's actions, bracket, extend to more players as needed, bracket. Identify each player's best responses, For each column, mark the rows that give player 1 the highest payoff dash. Those are player 1's best responses to that column. For each row, mark the columns that give player 2 the highest payoff dash. Those are player 2's best responses to that row. Locate cells that are mutual best responses dash a cell where both players' marks intersect. Each such cell is a pure strategy Nash equilibrium. Example dash coffee shop location colon. Two coffee chains bracket A and B bracket decide whether to locate in downtown bracket D bracket or suburbs bracket S bracket. Payoffs bracket profits in $1 million bracket colon. Row A D column BD gives 4, 4. Column BS gives 2, 5. Row S column BD gives 5, 2. Column BS gives 3, 3. Best responses colon. If B chooses D, A's best response is S bracket 5 greater than 4 bracket. If B chooses S, A's best response is S bracket 3 greater than 2 bracket. For a choosing D, B's best response is S bracket 5 greater than 4 bracket. For a choosing S, B's best response is S bracket 3 greater than 2 bracket. Intersection colon cell bracket S, S bracket with payoffs bracket 3, 3 bracket is the only mutual best response dash the pure strategy Nash equilibrium. Tips for MBA students colon. Use highlight or star symbols in the matrix to keep track of best responses. In games with more than 2 players, repeat the process for each player's conditional payoff tables. Remember that multiple equilibria are possible semicolon, each must be checked for the mutual best response property. Explanation colon. When a game has no pure strategy equilibrium, we look for a mixed strategy Nash equilibrium using the indifference principle. Each player must be indifferent among the pure strategies that receive positive probability in equilibrium. Step-by-step procedure 2-player case colon. 1. Assume player 1 mixes between actions a 1 and a 2 with probabilities p and 1 minus p. 2. Compute player 2's expected payoff for each of his pure actions as a function of p. 3. Set the expected payoffs equal for the actions that player 2 mixes. This makes player 2 indifferent, giving the value of p. 4. Repeat by letting player 2 mix with probability q on his first action. Compute player 1's expected payoffs. Set them equal and solve for q. 5. Verify that the mixed strategies make each player's unused pure actions yield no higher payoff, no profitable deviation. Mathematical illustration colon. Consider the classic rock, paper, scissors payoff matrix. 0 sum, win equals 1, lose equals -1, tie equals 0. Let player 1 play rock with probability p sub r, paper p sub p, scissors p sub s. Player 2's expected payoff for playing rock is e2 of rock equals minus p sub r plus p sub p. Lose to paper, win against scissors. Similarly, e2 of paper equals minus p sub p plus p sub s, and e2 of scissors equals minus p sub s plus p sub r. Indifference requires e2 of rock equals e2 of paper equals e2 of scissors. Solving yields p sub r equals p sub p equals p sub s equals 1/3. By symmetry, player 2 uses the same mix. Hence, the mixed strategy Nash equilibrium is each action with probability 1/3. Real-world analogy colons. In price competition, 2 rival firms may randomize between a high price and a low price. If one firm chose a high price too often, the other would undercut and capture market share. The indifference condition forces each firm to set the high price probability such that the opponent is indifferent between undercutting and matching. Key point for MBA exams colon. Write down the expected payoff equations, equate them, solve for probabilities, and then check that no pure deviation yields a higher expected payoff. Explanation. A dominant strategy is an action that gives a player a higher payoff than any other action, no matter what the opponents do. Formally, S sub I is dominant for player I if for every S sub minus I and every alternative S prime sub I, U sub I of S sub I, S sub minus I is greater than or equal to U sub I of S prime sub I, S sub minus I. A dominated strategy is the opposite. There exists another strategy that always yields a higher payoff. Relation to Nash equilibrium. If a player has a strictly dominant strategy, the Nash equilibrium will include that strategy, since it is the best response to everything. If a strategy is strictly dominated, it can never be part of any Nash equilibrium, because players will never voluntarily choose a strategy that is always worse. Example, advertising budget. Two competing firms decide each period to spend either $0, no ads, or $1 ads. Payoffs, profits. When firm A chooses 0 and firm B chooses 0, the payoffs are 5-5. When firm A chooses 0 and firm B chooses 1, the payoffs are 2-6. When firm A chooses 1 and firm B chooses 0, the payoffs are 6-2. When firm A chooses 1 and firm B chooses 1, the payoffs are 3-3. Firm A's payoff when it advertises 1 is higher than not advertising 0 regardless of firm B's choice. 6 greater than 5 and 3 greater than 2. So advertising is a dominant strategy for firm A. Similarly for firm B, the unique Nash equilibrium is 1-1, both advertise. Practical tip: in MBA case analysis, first scan the payoff matrix for dominant strategies. If either player has 1, you can immediately identify the equilibrium without solving best response equations. When no dominant strategy exists, players may need to consider mixed strategy equilibria or rely on concepts like iterated elimination of strictly dominated strategies to reduce the game before finding Nash points. Zero-sum game is a situation where one player's gain is exactly the other player's loss. The sum of payoffs equals 0 for every outcome. Two-player zero-sum games can be analyzed using the Minimax theorem von Neumann, 1928. Minimax equilibrium. Each player chooses a strategy that minimizes the maximum possible loss or maximizes the minimum guaranteed payoff. Formally, for player 1, the row player. Max sigma 1 min sigma 2 u tilde 1 of sigma 1 sigma 2 equals min sigma 2 max sigma 1 u tilde 1 of sigma 1 sigma 2. The value of the game, V, is this common number. Player 1's optimal mixed strategy guarantees at least V regardless of player 2's move. Player 2 can ensure player 1 gets at most V. Example: market entry. A large incumbent player 1 can either fight, incur high costs, or accommodate a new entrant player 2. The entrant can enter or stay out. Payoff matrix: incumbents profit, entrants profit. Rows are fight and accommodate, columns are enter and stay out. Fight and enter gives -2-2. Fight and stay out gives 5-0. Accommodate and enter gives 0-1. Accommodate and stay out gives 4-0. If we view the incumbent's profit as the payoff and the entrant's profit as the negative of that zero-sum simplification, the Minimax solution yields mixed probabilities that make the entrant indifferent between entering and staying out. The resulting equilibrium gives the incumbent an expected profit, the game value of about 1.5 million, and the entrant an expected loss of the same magnitude. Real-world analogy. In competitive bidding for a contract, the winner's profit is the loser's loss, the opportunity cost of not winning. Both firms randomize their bids to avoid being undercut. The Minimax solution tells them the optimal probability distribution over bid amounts. Key MBA insight. Zero-sum analysis is common in pricing wars, litigation, and competitive sports. Understanding the Minimax equilibrium helps managers design strategies that protect against the worst-case opponent behavior. Computation tip: solve the linear programming formulation. For player 1, maximize V subject to a sigma 1 greater than or equal to V bold 1 and sigma 1 in the simplex. For player 2, minimize V subject to sigma 2 transpose A less than or equal to V bold 1. Explanation: a Pareto efficient, also called Pareto optimal allocation, is one where no player can be made better off without making another player worse off. Formally, a payoff profile X is Pareto efficient if there is no other feasible profile Y such that U sub I of Y is greater than or equal to U sub I of X for all I, and U sub J of Y is greater than U sub J of X for at least one J. Comparison with Nash equilibrium. Nash equilibrium focuses on individual stability given the others. Strategies no player wants to deviate. Pareto efficiency focuses on collective optimality. Can we improve everybody's payoff simultaneously? Often a Nash equilibrium is not Pareto efficient. Classic example: prisoner's dilemma. The payoff matrix is cooperate versus cooperate yields 3-3, cooperate versus defect yields 0-5, defect versus cooperate yields 5-0, defect versus defect yields 1-1. The unique Nash equilibrium is DD with payoffs 1-1. Both players could be better off at CC with 3-3, which is Pareto superior, but not stable because each has an incentive to deviate. Efficiency analysis in business. In price competition, firms may settle at a Nash equilibrium, with low prices yielding low profits for all, akin to a Bertrand duopoly. However, collusion, though illegal, could move the outcome to a Pareto superior region with higher prices and profits. In public goods provision, the Nash equilibrium might involve underinvestment, while a socially optimal Pareto efficient level requires coordination. Why it matters for MBA students. Understanding the gap helps explain why regulation contracts or institutions are needed to move the market from a self-interested equilibrium toward a socially efficient outcome. Graphical illustration: in a two-player payoff space, draw the Pareto frontier, the boundary of feasible non-dominated outcomes. Plot the Nash points. You will see many lie inside the frontier, highlighting inefficiency. Derivation: pure strategy. Consider the following two-player normal form game. Find all pure strategy Nash equilibria. Solution steps: A. Write the payoff matrix. B. For each column, highlight player 1's best response rows. C. For each row, highlight player 2's best response columns. D. Identify cells where both highlights meet. E. State the equilibrium strategies and payoffs. What examiners look for: clear best response reasoning, correct identification of mutual best responses, concise notation. For example, S*1, S*2 equals left parenthesis L, R right parenthesis. Verification, mixed strategy. In the game below, determine the mixed strategy Nash equilibrium. Verify that each player is indifferent between the strategies they randomize over. Solution steps: A. Assign probability P to player 1's first action, 1 minus P to the second. B. Write player 2's expected payoff for each of his pure actions as a function of P. C. Set the two expected payoffs equal and solve for P. D. Repeat for player 2 to find Q. E. Substitute back to compute expected payoffs and confirm no profitable deviation. What examiners look for: correct algebra, clear use of the indifference principle, and a brief statement on why the mixed profile is a Nash equilibrium. Comparative statics: suppose the payoff of player 1 in the left parenthesis, a comma B right parenthesis cell increases from 2 to 4. How does the set of Nash equilibria change? Explain the intuition. Solution steps: A. Ray draw the payoff matrix with the updated value. B. Ray run the best response analysis. C. Note any new mutual best response cells and any that disappear. D. Explain that the higher payoff makes strategy a more attractive to player 1, potentially shifting his best response and altering equilibrium. What examiners look for: ability to quickly recompute equilibria, clear explanation of the direction of change, and linking the change to strategic incentives. Study tip: practice these three formats: derivation, verification, and comparative statics, because MBA exams often mix them in a single case question. Remember to label each step, keep algebra tidy, and always end with a short interpretation of what the equilibrium means for the firms involved.